As we begin section 4.2 on exponential properties and being able to simplify exponent and log functions, I do want to remind you that there are review materials loaded in to the homework section in your My Math Lab course. And so you may need to review rules for exponents, and you may need to review exponent and log equations if you need a little extra help. Now, what we're going to do is to make sure that we understand how to evaluate exponential expressions. And if you look at this first example, it's pretty basic. All we're going to do is substitute the value of x for this exponent. So this would become 4 to the negative 2 power, which would be 1 over 4 squared, which would be 1 over 16, or if you were to put that in your calculator, you could get a decimal value, but typically we don't do that unless we have been instructed to round to a certain place value. Now, on B, that would be 4 raised to the 5th power, which would simply be 4 times 4 times 4 times 4 times 4. It's a pretty large number. I'm just going to leave it written in exponent form right now. If we have 4 raised to the 2/3 power on C, that is something that would be irrational, because that means we would be taking the cubed root of 4, which is irrational, and then squaring it. We're just going to leave it with that fractional exponent. And if I were to take 4, I could actually raise it to the 2.15 power. And to do that, I definitely would have to put it in a calculator to see what it is. But that's all that we're doing, is we're just putting that value in for the exponent. Now, if we have the exponential function, some base raised to the x power, notice what our restrictions are. First of all, a has to be greater than 0, but it also says that a cannot equal 1. We do not allow 1 as the base for an exponential function. If you think about that for a moment, you'll probably understand why. What happens if I take 1 and I raise it to any power? Doesn't matter how many times I multiply 1 times itself, I still get 1. So it will not follow the rules for exponentiation as the others do. So 1 is not allowed as the base for an exponential function. Now, in order to solve this equation, we have an exponential equation that's very similar to what you would see if you looked at those examples that we practiced solving in the review for exponential and logarithmic equations. And the idea is that, first of all, I want to rewrite this, hopefully, first of all, so that I don't have any fractions. And if you recall, having a fraction reminds me that I can rewrite it by pulling what's in the denominator up to the numerator as long as I put a negative exponent. Since it's 125 to the positive 1 power while it's in the denominator, I could rewrite this as 125 to the negative 1 power. In other words, I can flip the fraction, and since it was raised to the 1st power, all I have to do is make the exponent negative. Now, the trick becomes I want to rewrite each side so that I can have the same base. 5, I'm not going to be able to change to anything else, but possibly 125 I could rewrite. And in fact, if I did the prime factorization with 125, I would see that 5 goes into it 25 times, and 5 will go into 25 5 times. That tells me 5 to the 3rd power is equal to 125. So I'm going to replace 125 with 5 to the 3rd, and then don't forget, there's still a negative 1 exponent on that. Using my exponent rules, what I know is that a power raised to a power means I multiply those exponents. So this becomes 5 to the negative 3 power, because 3 times negative 1 is negative 3. So I have now discovered that x must equal negative 3. Since the base is already matched, the only way this can be true is if the exponents are equal to each other. Let's look at the next example. if we were to solve this one, where we have 3 to the x plus 1 power is equal to 9 to the x minus 3, I don't have any fractions as bases, which is good, but I still want to rewrite these so that they would have the same base. And I know 3 can't, it's a prime number, it doesn't have any other factors to go smaller, but I could rewrite 9 as 3 to the second power. And if I did that and then put that x minus 3 for the exponent on it, now my bases match. What I notice on the right side is that I'm going to have to use the distributive property with my exponents, because a power raised to a power means to multiply those exponents together. So 2 times x minus 3 would give me 2x minus 6. And now that the bases are the same, the only way this equation can be true is if the exponents are also equal. So x plus 1 equals 2x minus 6. And I have a simple algebraic linear function to solve here. So if I were to subtract x from each side, that would give me 1 equals x minus 6. Then we add 6 to each side, and that means x equals 7. Now, a quick way to check ourselves is to go back, plug in to this equation. It should mean that 3 to the 7 plus 1 power would equal 9 to the 7 minus 3 power. Well, is 3 to the 8th the same thing as 9 to the 4th? You could put that in your calculator and you would see that yes, that does check out. Those will be equal. And if I happen to have a fractional exponent, such as I do in this problem, x to the 5 halves is equal to 243. Since I want to solve for x, I'd like to be able to get rid of the fraction exponent. And if I remember the property that says that a power raised to a power lets me multiply exponents, the easiest way to clean this up would be to raise each side to the reciprocal power. So if I flip 5 over 2, I'm going to get 2 over 5, and that becomes the exponent that I want to use on each side. So that would mean x to the first power, because if I multiply those exponents together, I get 10 over 10, which is 1, would be equal to, and it's your call on this, if you want to take 243, raise it to the 2/5 power in your calculator, you can simplify it that way. But if I were to take it back into radical form, then what I know is I'm going to take the 5th root of 243, and then I'm going to raise it to the second power. Now, what I will discover if I take the 5th root of 243, I can check this. If I add 2 plus 4, that's 6. 6 plus 3 is 9. If I add all those digits in 243, what I discover is I get 9, which is a number that is divisible by 3. That means 3 will go into 243, and it goes 81 times. Now, that's also divisible by 3, so if I go again, 3 goes into 81 27 times. And if I go again, 3 goes into 27 9 times, and then I'll have 3 times 3. How many 3's have I multiplied together to get 243? There are 5 of these, and remember, I'm looking for a 5th root. In other words, what can you multiply together 5 times to get 243? Well, the answer has to be 3. And if I take 3 and I square it, I'm going to get x equals 9. Now, to make sure that's right, if you take 9 and you raise it to the 5/2 power in your calculator, don't forget to put parentheses around your exponent if you're doing that, since it's a fraction, you should get 243. On the other hand, if right here, if you wanted to take 243 and raise it to the 2/5 power in your calculator, it should have told you the answer is 9. So those are some options on solving this. Now, we're going to do some interest problems. This is sort of the real-life practical part. If you purchase a car, if you're to buy a house one day, if you don't pay off your credit cards, all of those things require that you're going to pay interest And you want to be careful that you're on the right side of this. So understanding a little about how interest works is very important. Now, most interest today is compound. It's very rare you find anyone who is lending money and charging simple interest. And obviously the formula for calculating simple interest would be much simpler. Compound interest simply means you're paying interest on both the principal and interest that's being added in. And that causes the amount to grow faster. So if you're the person borrowing money, it means you're paying more in interest when the interest is compounded. If you're lending it, it's a good thing for you. You're going to get more interest back when you're compounding it. And this is the formula you need to know for interest that is compounded for a particular length of time, a measurable length of time that it is being compounded repeatedly. So let me just explain to you real quickly what these different variable means. P is going to stand for your principal or your starting amount. Principal or your starting amount. The R is probably pretty logical. That's your interest rate. The N, now this is the part where you have to be careful. It is the number of times in 1 year that interest is compounded. So for example, if they talk about interest being compounded annually, that would mean 1 time in a year. If it's compounded monthly, that would be 12 times in a year. If it's compounded quarterly, that means it's 4 times in a year. So you'll have to look carefully for what word follows compounded to be able to determine what N is. And T stands for time, and it's always in years. So if they give it to you in months, you've got to change it to years before you put it into this formula. Make sure you know what these different variables represent. I will allow you to have the formula when you test, but you have to know what those letters stand for those variables. Now, the first example we have says, suppose $2,500 is deposited in an account paying 6% interest per year, compounded semi-annually, which means twice per year. So we want to find the amount in the account after 10 years with no withdrawals. Now, I didn't tell you what A stood for, but we'll go ahead and put it on here. A is your final amount. So here's what we need to ask ourselves. Are we looking for the final amount in this problem? Yes, we are. Find the amount in the account after 10 years if there were no withdrawals. So what we need to do is to identify these other values. What would be our P, our principal or our starting amount? Well, that's got to be right here, $2,500. What is our R, our interest rate? It's 6% interest. Now, it's written with a percent sign, and most of the time in the problems it will be. You have to change it to decimal form. That means drop the percent, move the decimal 2 to the left, and it becomes 0.06. Always has to be in decimal form, okay? The N is how many times in a year will it be compounded, and it told us in the parentheses twice per year. And what is going to be our T value? What length of time are we going to allow it to compound? 10 years, and that's already in years, so we'll use 10 for T. Now we have our formula. A equals P times 1 plus, we'll take R divided by N and raise it to the N times T power, or T times N power. And if we plug in, we're going to have 2,500 times 1 plus, the R was 0.06, over the N was 2, and we're going to raise that to the 2 times 10 power, which is going to be 20. And at this point, it's just a matter of going to your calculator. Be sure you enter things carefully. Using order of operations, we know we need to solve for what's in parentheses first. So if I were to take 1 plus, and then in another parentheses, I'm going to put 0.06 divided by 2 so that the calculator understands that it needs to take 0.06 divided by 2 and get that answer before it's added to 1. I'm going to have 1.03. Now, it won't always work out to be a number that's this neat, so be careful that you don't round too soon. And now I have that number raised to the 20th power, and I also have times 2500. If I think about order of operations, you have to take care of exponents before you can multiply. So raise 1.03 to the 20th power, and you do get this long decimal number that I will then multiply times 2500. And since I am looking for a final amount, I need to round according to money. So if I'm rounding according to money values, the smallest value of money we have is a penny, which is 2 places to the right of the decimal. This should end up being $4,515, and if I look to the right of the decimal, I have 0.278. If I round 2 places, that's going to become 28 cents. And that would be my answer. Next example, we're going to see there's a follow-up question. How much interest is earned over the 10-year period? Now, interest is what you would get paid for letting them use your money. So what do you think would be the easiest way to calculate the amount of interest that was earned? Well, that's pretty simple. All I would have to do to get the amount of interest is to take the final amount and subtract the principal from it. So the final amount we just came up with was $4,515.28. And we're going to subtract the $2,500 that we started with, and what we end up with would mean there was $2,015.28 earned in interest. So our money almost doubled in 10 years when we had a 6% interest rate compounded semi-annually. Now, we won't always be looking for the A value. This asks us to find the present value, or the principal, the starting amount. Good old Brendan Berger, he has come up with something that is requiring him to pay a lump sum of $15,000 in 8 years. So for whatever reason, he knows he needs $15,000 available to use in 8 years, and he has some money now. He needs to figure out how much he would have to deposit today. In other words, we're going to look for what that present value or that principal amount would be at 4.8% compounded annually. That would be his interest rate. That would give him $15,000 in 8 years. Now, remember, we still have to figure out what we're going to be solving for. In this particular problem, it's asking us to find the present value. So we do not know what P is. But we know how much money he needs at the end of 8 years. He needs $15,000. Okay, what would be that interest rate? Well, it's 4.8% compounded annually. Remember to turn it to decimal form, and that would be 0.048. The N tells how many times in a year it's being compounded. Since it's compounded annually, N is 1. And what is the length of time he has to invest? 8 years. So T is 8. Now, let's go to our formula. A equals P times 1 plus R divided by N, all raised to the N times T power. And we're going to plug in the parts we know. We know A is 15,000. We're looking for P, so I'm going to leave P, N as a variable. I'm going to have 1 plus, now since R is 0.048, but N is 1, that's actually going to clean up to be sort of a nice fraction is just going to be 0.048, which will add to 1. But then we have to raise it to the n times t power. Well, 1 times 8 is 8. Now, again, thinking order of operations, I've got to clean up what's in the parentheses first. So I have the 15,000 equals p times 1.048, when I add that together, raised to the 8th power. So here's what you would need to do in your calculator. You're going to have to take the 1.048 raised to the 8th power, and remember there's going to be a lot of decimals there, but we're dividing each side by that. So I have to take that answer and divide it into 15,000. So depending on the type of calculator you're using and the way that it is set up, if I were to take 15,000, divide it by that answer that I just got, I come up with $10,308, and when I round to the nearest penny, I'm going to get 63 cents. So that's how much Brendan Berger would need to put into a bank account if that's the interest rate that he can earn. Now, here's his problem. He only has $10,000 available to deposit right now. So he needs to look for a little better interest rate. Do you think we could figure that out? Hopefully you say, yes, we certainly can. We're just going to now have to look for a different variable in our problem. So if we stay with our formula, A equals P times 1 plus R over N to the NT power, he still wants $15,000, but he only has $10,000 that he can invest, and we're trying to find what the interest rate is. So we don't know what R is, but we're going to assume that nothing else changes. It's still going to be compounded annually. So R over 1 is just R. And if N is 1, then 1 times 8 is still 8 for our N times T, for our exponent. Now, be very careful on this. We're solving for R, but it's inside that parentheses. So we need to start peeling off anything we can that is not part of the parentheses. In other words, this parentheses, besides being raised to the 8th power, is also multiplied by 10,000. If I divide each side by 10,000, then I make this right side a little bit simpler. I get a little bit closer to where R is, and 15,000 divided by 10,000 would be 1.5 equals, and then I have 1 plus R in parentheses raised to the 8th power. Now, think for a moment. We got rid of an exponent earlier by doing what? Raise each side to the reciprocal power. So let's raise each side to the 1/8 power. Because if I raise a power to a power, I multiply those exponents, and 8 over 1 times 1 over 8 is just to the first power, and I'll have 1 plus R on the right side. Now in my calculator, if I take 1.5 and I raise it to the fractional exponent 1/8, then I end up with a decimal number that is pretty long, since I'm looking for an interest rate, and it looks like in decimal form we were going 3 places to the right of the decimal. Then I would say, let's round this thing 3 places to the right of the decimal, and I would have 1.0519, and because there's a 9 that follows the 1, it's going to round to be 1.052. So check your calculator to make sure that's the value you're coming up with. I'm almost there. To find R, all I have to do now is subtract 1. And if I were to subtract 1, then R would be equal to 0.052, which if I put it back in decimal form would be 5.2%. That would be the interest rate that he would need to look for if he wants his $10,000 to grow into $15,000. Now, that's one type of compound interest. That's when we see a word after compounded that talks about a measurable unit of time. In other words, n is a number of times in a year that we can count up that the interest will be compounded. But more and more often you will find that interest won't be calculated that way. Instead, it's compounded continuously. If you haven't figured this out yet, the more often you're compounding interest, the more money the lender will make. So most of the time you're going to find, or often you're going to find, that interest is compounded continuously, which means there's not a particular number of times. We can't count it if it's continuous. But an interesting thing to notice, no matter how many times it gets compounded, there's sort of a leveling off that occurs. And so if we were to consider this, and notice this says, suppose that $1 is invested at 100% interest per year, okay? So in other words, each year your money earns 100% in interest, and you compound it n times per year. Let's see what happens the more often that we compound it. So if you look at our formula, since R is going to equal 100%, but when you change that to a decimal number, it becomes 1. Look what happens if we were to plug into this table. We would have, when n is 1, we would have 1 plus 1 over 1 raised to the first power, which is 2, which makes sense, because if our money is going to earn 100% interest, that means it's going to double in 1 year. But now, if n is 2, we're going to have 1 plus 1 over 2, and that gets raised to the second power. And if we were to put that in, we would come up with a number like 2.25. So we can see we're earning a little bit more if we increase the period of time for compounding to 2 times a year. Now, let's just kind of skip forward. We're not going to do all of these, but we'll do enough where you can see the pattern. If I were to use 10, we would have 1 plus 1 over 10 to the 10th power, and that would be 2.59 if I go 2 places to the right of the decimal. In fact, it would be 2, let's go 3 places, 2.594 if I go 3 places to the right of the decimal. Let's see what happens with 1,000. 1 plus 1 over 1,000 raised to the 1,000th power. That will equal 2.717 if I go 3 places to the right of the decimal. And let's look at the last one. 1 plus 1 over 1,000,000 raised to the 1,000,000th power. If we were going to compound this 1,000,000 times in a year, and you're going to get 2.718 ... Now, what you may not recognize, and I know that took a little bit of time, but what I want you to see is we've got this leveling off that's beginning to occur here. It went from 2 to 2.25 to 2.594, but look at these last two. They're pretty close together. So no matter how big we're getting, we're sort of approaching a particular number, and that number is E, which has a value of 2.7182818 ... How about that? Now, that means this natural number E is very powerful, and it occurs often in nature, but it's also used many, many times in these formulas for compounding interest. So if we want to compound interest continually, then we're going to use this formula. Most people say A equals PERT. It's the principal times that natural number E that's raised to the RT power. So you recognize the A, you recognize the P, the R, and the T from our previous formula. Notice there is no N here. That's because we don't have a particular number of times in a year that this thing is being compounded. Instead, it's compounded continuously, and that makes the base the natural number E. So, look at our example. Suppose $8,000 is deposited in an account that pays 5% interest compounded continuously. There's clue number 1. Look for the word that follows compounded. If it's something that's a measurable amount of time, you use the other formula. If it says continuously, you're going to need A equals PERT. Now, what we're doing is compounding it continuously for 6 years, and we want to find the total amount on deposit at the end of 6 years. So that means we're looking for the A. We want the amount at the end of 6 years. How much did we put in? $8,000. So our P is 8,000. E is a number, a natural number, and there is a button on your calculator that should have the E, and we're going to raise it to the R times T power. Now, R said we were going to pay 5% interest compounded continuously. As a decimal, that's 0.05. And the period of time that we're going to have it on deposit is 6 years. And again, T is always in years. So all you do is go to your calculator, and you're going to multiply 8,000 times, find your button that has the E, and then you would have to raise it to, and in parentheses, you would want to put 0.05 times 6 for your exponent. So once we complete the calculation, we will find that that final amount is $10,798.87.